All right, let's look at some of these trig equations here. Essentially what you want to be doing for the first one, which you can read right there, wants you to solve for solutions. It doesn't actually want the numbers, just wants the number of answers that you have. We're going to solve two different things. The first thing, we're going to take this bracket, sine x minus 1, and we're going to solve when that's equal to 0. So let's do that. Sine x is equal to 1. In order to find my angle x here, you take the inverse sine of both sides, and which we know from the sine graph, kind of looks like that, up the top in the corner there, that sine of 1 is pi on 2. There's only one solution for it within the domain right there, between 0 and 2 pi. We can also do the second one for the same for tan. Tan x plus 2 is equal to 0. Subtract 2 from both sides. Take the inverse tan of both sides to find the angle. Now, because we don't actually care about what the answer is, we're looking at the number of solutions that we have. Tan is negative in the second quadrant and the fourth quadrant. So it will have two solutions. So you may think the obvious answer is that it's going to have three solutions. This is actually incorrect, because if we take pi on 2, if I put pi on 2 into the equation here, I get 0 times whatever tan pi on 2 plus 2 is. But tan pi on 2, or tan of 90, is undefined. It doesn't exist. So therefore, we don't actually have three solutions. We only have two solutions, because the solution for sine x minus 1, it doesn't actually exist. We can't do tan pi on 2. So this is one they do. It's a little bit tricky to kind of trick you out a little bit. That's how that ends up working. So there are only two solutions, and they are whatever the inverse tan of negative 2 is. You can find them if you like. The numbers are going to be ghastly. You're going to look at a similar idea for the one below. This time it actually wants the answers. Oh no, same thing, just wants the number of solutions. We can actually find the solutions for this one, so let's do that, because the number's going to be pretty nice. So we've got two things. With the absolute value, it could be cos of 2x is equal to 1, or cos of 2x is equal to minus 1. Now, whenever we see that x has a coefficient in front of it, or the angle does, I always like to let u equal 2x. Now, you don't have to do this, but it just makes it a little bit more of a process, and it makes it a little bit easier to solve. So if we let u equal 2x, put u back into that domain there, so that means x is u over 2, so we have 0 between u over 2, between 2 pi, or 360, times everything by 2. We are solving between 0, u, and we are also solving between 720, which is the same as 4 pi, which means it's going to go around the circle again. Always helpful to be looking at this. So we're going to be solving cos of u is equal to 1, and cos of u is equal to minus 1. Now, cos of u is equal to 1, if you remember from the cos graph, which looks like this, it is 1 at when u is equal to 0, and 360, or 2 pi, which is what we're going to call it. Cos is negative 1 only at that point down there. That point down there is pi. So if we solve the other one, u is also equal to pi. Now, because we've solved for u, what we need to actually do is we need to consider the domain all the way up to 720, all the way up to 4 pi. So what that means is we need to add 360 degrees or 2 pi to both of these answers as well. So u is going to be 0, 2 pi, and 4 pi. Notice how if we go 0 plus 2 pi, I end up with 2 pi. I don't need to write it twice. You can just write it once. And then on the other side, we've got u is equal to pi and 3 pi. So those are going to end up being my answers. We're going to reverse engineer this. We're going to put u back into here. So I've got 2x is equal to 0, 2 pi, 4 pi, and 2x is equal to pi, and 3 pi on 2. Oh, no, just 3 pi. Now, because I've got 2x, I want to solve just for x. So I'm going to divide everything by 2. 0, pi, 2 pi. And then on the other side, I've got x is going to be equal to pi on 2 and 3 pi on 2. 1, 2, 3, 4, 5. That gives me 5 solutions, which is the actual answer that we end up with. Now, the other one that is a little bit tricky is it wants the domain of this chestnut. Oh, x plus pi on 4. Now, the domain of this, normally, we can take a look at, we know that the domain of cos kind of goes forever. The range is what changes a little bit here. This is going to be a little bit different. And the reason it's going to be different is because the domain of let's look at the domain of sec x or sec theta. We're just going to call it sec theta for now. Let's do that. Let's just go let theta equal x plus pi on 2, and we'll come back and deal with the rest of it later. The domain of sec theta, sec is 1 over cos theta. Already, we're going to have values of theta that are going to give a problem because we can't divide by 0. So anytime that theta or cos theta is equal to 0, we're going to have no solutions from this. It's just not going to work. It's not going to fly. So if we take a look at when cos of theta is equal to 0, from my beautifully drawn graph right there, you'll know, and if you don't, it's fine, that it's pi on 2 and 3 pi on 2. Those are the values of cos that don't exist, that they're not going to work. We can't do it because cos of pi on 2 or cos of 90 is 0. 1 divided by 0 is problematic. So we've got a list of values that it can't be. And having a list of values that it can't be is going to be very, very helpful. So it's got asymptotes at when theta is going to be equal to pi on 2, 3 pi on 2, and you can kind of like keep going from there, 5 pi on 2, etc., etc. But because we looked at pi on 4, let's resub that back in. Because we looked at theta. Now let's look at x plus pi on 4. Remembering that this goes forever. Now, let us take a look. Let's subtract pi on 4 from everything that we've got. X is going to be equal to... it's going to be pi on 4. I'm just typing these out so I don't get them wrong. 5 pi on 4. And you can see where the trend's going to be going from here. 9 pi on 4, etc., etc. What you're essentially going to be doing is you need to put this into a rule for the domain. So what the domain's going to end up being, these are the x values that it can't take, and that's kind of what we're going to be looking at it. So let's put this into a rule where k is an integer. That rule is going to end up being like what it says, 4k plus 1 pi over 4. Because what we're going to do is if I put 1 in there, I'm going to get 4 plus 1, 5. If I put 0 in there, 0 plus 1 pi on 4. Negative 1 would go backwards. So that is what it ends up being. That ends up being my rule for the domain of what we've got, because this right here is essentially what we can't have. So I hope this helped. That's it. Any questions, let me know.